We are all terrified of earthquakes, am I right? They are essentially surface waves and release large amount of energy and momentum, causing havoc to the buildings, etc. on the surface of Earth. But do you know that we all carry miniaturized nanoscale earthquakes in our pocket all the time? Yes, our smartphones have surface acoustic wave components which are used to filter and process signals carrying information at gigahertz frequencies from our phone to the radio tower. These miniaturized earthquake-like waves travel on the top surface of piezoelectric materials by the conversion of an electrical input into a mechanical force. To understand it better, let's take a quick example of piezoelectricity. The gas lighter that we commonly use produces fire only when we mechanically push the button on it, which in turn stresses a piezoelectric crystal, producing a high voltage pulse which creates the spark. Now, surface acoustic waves can transfer energy into their neighborhood, like earthquakes, and control the fundamental properties of surrounding material. They can also sense the changes in the surrounding, like changes in pressure, humidity, temperature, light, etc. Now let's delve deeper into optical application. Suppose a light source, like a laser, is applied upon a semiconductor material. The light source will generate electrical charge carrier pairs, which are responsible for all the basic functions in our optoelectronic gadgets, such as in a camera, OLED screen, or a solar cell. These pairs of electron and hole are commonly called as excitons and are required to be transported efficiently for maximum performance of the electronic component. If a surface acoustic wave flows through the semiconductor material in presence of the laser, the wave field would separate these pairs into separate charge packets and carry them forward. My current research focuses on such behavior in lesser studied emerging semiconductor materials, such as solution processable semiconductors like organic polymers and perovskites. These are of low cost, mostly found in powder form, and can be transformed into a solution by doing simple process, and finally deposited easily by drop cast or spin coating. The whole process is in contrast to the typically used crystalline semiconductor materials. So these materials, like the organic polymers and perovskites, are easier to handle, cost-effective, and environment-friendly. And with surface acoustic waves, we can potentially improve the transport efficiency and come up with new interesting functionality.
Good.